Hello and welcome to this talk on DynamoDB. The official title is Building Modern High-Performance Applications at Any Scale with DynamoDB. If that's what you're looking for, you've come to the right place, or at least you've clicked the right link. I'm Jason Hunter, Principal Solution Architect at AWS with a specialty on DynamoDB. What we're going to talk about today, we have two talks in two parts. The first part is for beginners. That's where we are right now. We're going to talk about the purpose of DynamoDB, where it came about and why and how, what its main features are, the value it provides to you, and we'll get started with its key concepts. In the second section, we'll crack it open, look under the hood, and see how it actually operates and how it does what I say in this section it does. All right, so let's get started. DynamoDB came about, we could really trace it back to 2004. In 2004, Amazon.com had been growing for many years, and it had an outage. The outage was caused by database issues. It just had grown too large for the relational databases that it was built on. And that caused engineering to think, what can we do? We don't want to stop growing. We need to keep growing. And look at it. That was almost 20 years ago. So they've been successful. How do we continue growing? We can't do it on relational. So they put their minds to it and they realized, maybe we could do something that was non-relational. And they wrote this Dynamo paper in 2007. And that was part of the tidal wave of NoSQL databases that were coming on the scene at that time. The idea being, maybe instead of having everything relational, we could have more special purpose databases, and DynamoDB being something for high scale systems like Amazon.com. And it got provided as a service in January 2012. This is over 10 years now of general availability. And so now people who aren't Amazon.com, but just AWS customers could use DynamoDB, the same system that Amazon.com uses underneath. And today it's a tier 0 service, which in AWS means it is a service on which other services can be built. So other aspects of AWS use DynamoDB to do their state management. So if you're going to spin up an EC2 box, you're using DynamoDB, even if you're not directly using DynamoDB. And so databases these days are a bit different. And I list here several things that have changed. And if you have a use case that needs one of these things, DynamoDB is able to handle it. And maybe you don't have all of them, but maybe you do. And one of it is that maybe you have users, massive numbers of users, more than millions of users. That's something that wasn't as common in the older days. Nowadays, pretty common. You have data volumes in the terabytes, petabytes, or even exabyte ranges. You may have globally distributed customers. You might want extremely fast performance. You might want to be able to guarantee millisecond or even microsecond performance when you make some invocation against the database. And you may want to scale up to the millions of requests per second. That's something you can do with DynamoDB. And when you're doing that, you don't always want to keep at the highest level. You might want to scale up to be able to handle the millions of requests, but then scale down during the lower times. And that's something that DynamoDB lets you do as well. I'll explain. And when it comes to how do you get charged for a database that scales up and down? Well, the idea is you do pay as you go, like an electric bill. The more you use, the more you pay. But if you stop pulling electricity, you stop paying for electricity. And the database works like that. You're not thinking about servers anymore. Well, at the same time, you want to get started, instant API access. You just click a button and you've got your first DynamoDB table. It's that easy. And so as a result, over these 10 years, hundreds of thousands of customers have chosen to use DynamoDB. And I list a few of them here. If you're curious about any one of them, just Google that name, case study DynamoDB, and you'll find it. They're all available on the web. And I will actually tell you about a few of these as we go along. Sometimes I think, or I wonder, how many times in a day do I do something that interacts with DynamoDB? And it's amazing. This is some of the use cases of what our customers and possibly people that you interact with are doing with DynamoDB. So let's say I log into Vanguard and I make a trade, probably using DynamoDB. Let's say I relax at the end of a long day and play some Plants vs. Zombies. That's using DynamoDB. Let's say I take an Uber or a Lyft somewhere. That's using DynamoDB. Or I read some news article that's showing at the bottom other things I might be interested in. That's pulled from DynamoDB. Or I shop on Amazon.com, DynamoDB. Or I relax at the end of a day and I Netflix and chill, or I use Disney Plus, DynamoDB. All over the place, these kind of applications are using DynamoDB as their main data store. And so, what makes DynamoDB unique? And I've divided it into 3 pillars, and each one of these I'll delve into in some depth. The first one is performance, being able to handle really massive amounts of traffic with consistency, low latency. Second, serverless design. It's not just a managed service, it's serverless. You never see a server on the back end. It's maintenance free from your point of view. The more traffic you send, the more capabilities are given to you. You pull back, that's fine. You send more traffic, more capabilities are given to you. That kind of dynamic adjustment is a core feature of DynamoDB. And last, a good set of enterprise features, and I'll explain all of them in some detail, but it's not just a simple key value store. It has a lot of really robust enterprise features. So let's look first at performance. This is a live chart from a social media customer that was supporting, times when people would post during the Super Bowl. This was Super Bowl 2017. And you can see the traffic pattern go up and down as people are saying that was an amazing play or gosh darn it. And the big spike there, that's the end of the game when people just couldn't wait to post. And what you see is the capacity was provisioned at 5.5 million write capacity units per second. All right. And so they were just able to say to the database, this is the traffic I expect. All right. So that's about 5.5 million postings per second. At the end of the game, it went up above 10 million. And that's okay. Even above provision capacity for short durations is fine. And they didn't have to call AWS and say, hey, the Super Bowl's coming up, expect something. They just specified the provision capacity and they had temporary bursts above it. That was all fine. So this kind of, lots of users, amazing amounts of performance is one of the intrinsic features of DynamoDB. This slide shows a synthetic test where instead of real user data, we on my team just sent more and more traffic at the database because we were curious, what happens to the latency? DynamoDB is good for low latency requests, but what happens as you push more and more traffic at it? So we pushed, the font is tiny, but on the left it says 300 million. That's per minute. So that's about 5 million requests per second. So pushing 5 million requests per second peak, what you see on the right from CloudWatch is the latency of those requests. It went down. The harder the database got hit, the faster it ran the queries. Not many databases can say that, right? Throw as much traffic as you want at this database. It'll be fine. In the second section, we'll talk a little bit about why that is, in case you're thinking, how is that technically possible? In the advanced section, we'll cover that. Now, if you're thinking millisecond is great, 3 milliseconds is good, but I want faster, and I could imagine some of you are thinking that, you actually have an option for that, which is DAX. DAX is the DynamoDB Accelerator. And this is an in-memory cache that you can put in front of the database. So frequently requested items will be in the cache, and you can get back millisecond latency in microsecond latency instead of millisecond latency. Now, you can do other kinds of caches. You could do a Redis cache, and that's fine. What's interesting about DAX and why you might want to choose it is it has the exact same API as DynamoDB itself. So you don't have to change your code. You just point at a different endpoint. And if you do a read, if it doesn't have it in the cache, it pulls from DynamoDB into the cache and gives it to you. If you do a write, it remembers what you wrote, but also pushes it into DynamoDB for persistence. So it's just an invisible layer. I don't know if invisible is right. It's a dynamic layer that can be added API compatible in front of the database. Something that if you have kids that play video games, it's great if your database is fast, but latency and ping times is what it's all about, right? My kid was bragging the other day that he was playing someone who was better at Fortnite than him, but that poor guy had 100 millisecond ping times. He never stood a chance. So my kid annihilated him. Why? Because the server that they went with was closer to my son than to the other guy. And for that kind of reason, when you have really high performance needs, you want global replication of the data. You want copies of the data in different geographies. DynamoDB actually makes this really easy because you use what's just built in as global tables. It's push button setup. You say, I want this table in this region and this region and possibly some other regions. And automatically it will stream and synchronize the data between them. And it's active. So you can write to any of those databases and it will synchronize the data to the other regions. And then you can read from whatever region is closest to you or your users. This is great to not even have to do any rewrites. The stack that you have in any particular region can just connect to its local DynamoDB, and it's part of a global distributed database. In case you're curious, if there's a conflict, it's last write wins, right? So If you write at the same time, two different places, the one that was the later millisecond is the one that wins. So let's look at a case study. And I think one of the best case studies to look at this is probably Amazon.com. And I'll actually give you two case studies for Amazon.com. One is that DynamoDB supports the Amazon.com sites, Alexa, and all the logic going on inside the fulfillment centers. It gets really most stressed during Prime Day. And during the 2020 Prime Day, during 66 hours, these sources made 16.4 trillion calls to the DynamoDB API, peaking at over 80 million requests per second. I've done databases for a long time. 80 million requests per second still makes my eyes open. Another example is that Amazon uses the Herd system. This is order workflow orchestration. So from the time you say you want to buy something to the time it delivers to your door, this all goes through what's internally called as Herd. That was built on Oracle. And once again, we were hitting limits of how efficient this could be and how complex it got. It was up to 300 Oracle hosts, and it was just becoming more of an operational burden. So by switching to DynamoDB and going to the serverless idea, it got better both in delays, which went from 1 second to 100 milliseconds, and scale in that the operational burden went down tenfold. Just because it looks to the end user of Herd like there's an endpoint, a web endpoint that you can do inserts and gets and queries and scans and whatnot. You're not aware that there's any servers on the back end. That's been isolated. No more thinking about 300 Oracle hosts. So let's dig in a little bit about the serverless nature. All right. This slide shows the things you don't have to worry about anymore. That's a pretty good list. You don't have to think about operating systems and database patching and racking and stacking and keeping up with a failed disk or a failed server or issues replicating around the world. You can get 5 nines out of DynamoDB and not have to worry about any of this. So how do you pay for a service that doesn't have servers? How's it charged? Well, the idea is that you pay for what you use, basically. And there's a couple different modes. I'll explain them. The first one, the simplest one to understand, is on demand. You pay by request. You don't have to say in advance what you expect is coming. This works great when it's bursty, when it goes really high, and then it goes maybe down to 0. You just pay by the request. And the pricing in US East 1, Northern Virginia, is 25 cents per million read requests, read capacity units, which is a unit of read, and $1.25 per million write capacity units, which is a unit of write. So you do 1 million, you pay a quarter, that kind of thing. Really straightforward. And if you aren't making any requests, you pay 0. You just pay a storage for the amount of storage in the database, but you don't pay anything for throughput. So that's on demand, really convenient. There's another, which is provisioned. The idea of provisioned is you say in advance what's coming. And we saw that with the Super Bowl example. They provisioned 5.5 million writes per second. Why would you pick provisioned? Well, it's just cheaper on a per request basis. All right, so if you do 5.5 million, that's great. And you pay less per request because you've given AWS some notice of the throughput you expect to be going through. And so if you have flat traffic, that works really well. But what if you don't have flat traffic? Maybe you see what is on the slide here. Traffic goes up, traffic goes down, traffic goes up, traffic goes down. Well, that's okay. For that, you have auto scaling. Auto scaling you can turn on and you say to DynamoDB, I never want you to go below here. I don't want you to go above this, but in between, I want you to dynamically adjust based on the traffic you're seeing. And you see that here, as their traffic went down, it reduced their provisioned writes. As their traffic came up, it increased their provisioned writes. And that reduces your cost because it's better than if they'd allocated at, say, 12,000 here. It's dynamically curve fitting. And so if you have a sense of your usage pattern, or if your usage pattern is more like a wave, use provision capacity. If it's spiky and you say, I might go from very little traffic to very high traffic because I'm going to do a bulk load, well, you have the choice. You can be an on-demand, or you can provision yourself dynamically and say, provision big right now. I know right now I'm doing a load. I know right now I'm doing a launch day. You can give the database some notice that that traffic is coming. To do a case study on the idea of provisioned and on-demand and serverless, let's look at Disney. So we're all aware of Disney Plus. We all love Baby Yoda. Disney Plus is a big user of DynamoDB. And they do a wide variety of things. They track recommendations. They track your watch history, so they remember what you've seen. And they also track bookmarks. Now, what's a bookmark in a streaming platform? A bookmark is where you last were on every show. So you can see even on the screenshot, there's some blue lines and you're halfway through Free Solo or whatnot. That's a bookmark. They're continuously tracking for every user, every piece of content, what's your latest progress on that. And the quote here says, billions of bookmarks ingested today over Amazon Kinesis and into Amazon DynamoDB. So it's a good example for this. They've got, at the time of this slide, it was 60.5 million subscribers. Now it's well over 100 million. So they have a multi-region deployment using global tables. They can write to any of the regions. So when you're bookmarking, you're probably writing and reading from the nearest region to you as their customer. And they use on-demand and provision back and forth. When they open up a new region and they don't know what the traffic will be, they go to on-demand. They just say, whenever I make a request, I want you to be ready for it. And otherwise, they can reduce costs by going to provision mode and giving more of a hint. All right, we think the traffic will be around this range. Please auto-scale around that range. And so this is a good example. Netflix does similar. At this point, we've covered performance and we've covered serverless. Let's look at some of the enterprise features. The first one I think we should cover is ACID transactions. A lot of people will say NoSQL databases don't have ACID transactions, and that's not true. DynamoDB definitely has ACID transactions. ACID stands for atomic, consistent, isolated, and durable. It's basically a way to say, here's a set of things I want you to do to the database, a bunch of mutations. I want them either all to happen or none of them to happen. Think about moving money from one account to another. You don't want to half move the money out and have the issue be that the request failed halfway done. You either want the money to come out and go in or neither. Or say in an online game, you're buying a sword. You want to reduce their money at the same time you add the sword, not just one half. And so before, this is an addition I think is about 5 years ago. Before you had to do this in your own code. It was difficult. Now it's built into the database. It's easy. So the developer has less to do, and it makes it a lot easier to migrate over legacy applications that maybe are depending on ACID semantics. When it comes to security, let me tell you a few things. First is about encryption. Your data is encrypted. You actually can't turn off encryption. It's encrypted on the wire. It's encrypted at rest. Your choice is, do you want the default encryption where DynamoDB manages it, or do you want to use a KMS? And if you use a KMS, a key management system, you can have AWS manage the key, or you can have a customer managed, a customer provided key. I show a screenshot here of you being able to pick between those three choices, but it's always encrypted. Another nice thing about DynamoDB is that it's integrated with IAM. So you don't have passwords to the DynamoDB system. You just have roles on the client, an EC2 or a Lambda or whatnot, and the roles grant the access. They decide which tables you can see, what actions you can do, which items inside the table you're able to access. And so that's convenient. You don't have to worry about passwords and credentials. And I did want to give you one pro tip. If you're accessing DynamoDB from a VPC, you probably want to set up a VPC endpoint, which allows you to connect to DynamoDB over a private link connection. And that way your traffic is staying entirely on Amazon's backbone. Just a good tip. One of the interesting things you can do is audit basically everything. You can audit the control plane operations. This is when you create a table, get a table, list the tables, things like that at the table level. You can also capture data plane operations, all the times you've inserted content or retrieved content or run a query. Now, why would you do this? In some situations, you need to do it for compliance. Sometimes you want to say, did anyone access this celebrity's data? You can go back to the logs and check. Go into CloudTrail, you'll be able to see who accessed this, who changed this. You can look for someone doing something nefarious for data exfiltration. You can look for anomalies. You can analyze, is anyone accessing something they're not supposed to? Was there a loophole in our IAM configuration which allowed a get where we didn't expect a get to be successful or was actually returned? So it's optional, but you turn it on, you're able to pick what you want to audit, and it will create audit logs of all the activities going on inside DynamoDB. Another enterprise feature, backup and restore. When you think about backup and restore, you're not responsible for a backup to make sure that the data isn't lost. There's not a server that's going to lose the data, right? So it's not like typical backups of a database where the database is over there and I need to do a backup lest I lose my server. You won't lose your server. It's replicated automatically by AWS on the back end to multiple availability zones. But there are reasons you might want to do a backup. One is compliance or archiving reasons. You want to take a snapshot of the database as it was at a particular time so that you can always refer back to it, right? And so for that, you can do an on-demand backup. Just hit a button or invoke a command line or an API call. Kind of a cool trick. There's no performance impact when you do that. It doesn't slow the production workload. You just hit the button and it knows how to do it without having to slow down the database. Another backup option is continuous point-in-time recovery, which we call PITR. This allows you to go back in time to any second over the last 35 days. Why would you want that? You want that because maybe someone makes a mistake, right? Someone deletes an item, modifies an item, and later on you realize, oh, that application made a mistake. It shouldn't have done that. You can now save your bacon. You can go back in time to before that mistake happened anytime in the last 35 days. So that's another reason to do a backup. You can combine the two. It also integrates with AWS backup if you have a centralized, for compliance reasons, especially a centralized backup interface to all your different databases. DynamoDB, as of November last year, is able to do that. Something to be aware of, it's less an enterprise feature and more a nice tool, is NoSQL Workbench. This is a GUI that runs on all the major operating systems. With it, you can do data modeling. You can enter in some data that you think would be kind of useful to visualize. And then you can look at your data and say, all right, what would my queries look like against data that had these indexes and this kind of shape? And in fact, you can, with Operation Builder, get sample code that does the request that you want. Oh, you use Python, you want to do a get item? Hit the button. Here's the Python code that shows you how to get started using DynamoDB. So that's really convenient for people who are new to DynamoDB. I recommend NoSQL Workbench. I'll show you some screenshots of NoSQL Workbench here. This is the visualizer of the ski resorts data model. The NoSQL Workbench comes with a variety of sample data sets. This is, well, I like skiing, so I picked this one. You see there's some data about lifts. Lift 3, lift 23, lift 16. And about each lift, we have timestamps of different days, the riders that they had, the snow coverage of inches and things like that, as well as some static data about that lift itself. And this is the kind of modeling that you do in DynamoDB, where you have keys and you have attributes, and you'll notice that every item might have different attributes. So it's a little different than a relational database where every item in a table is always exactly the same. And in here, you can say, this is what I want for my key, and this is what I want for sample data, and you can look at different points of view. Another enterprise feature is the ability to export to S3, S3 being the simple storage service. Why would you do this? Well, let's say you've got a table and you want to do analytics against it. DynamoDB is not for analytics. DynamoDB is for transactional workloads, OLTP. So if you want to do analytics, you want to export from DynamoDB, put it into another system. You can use Athena directly against the S3 files. You can put it into Redshift, you name it. But this ability to hit a button and have your data exported to S3 is a great way to jumpstart a variety of data lake type projects. So long as you've enabled PITR, which is that point-in-time recovery, you can do this. And once again, no impact on performance. So you can say, I want to export to S3. It's a bulk parallel process that goes on in the background, as easy to start as hitting a button, and it doesn't slow down your production workloads. At the end, you'll have a good number of files inside of S3, which you can decide, what do you want to do with it? Do you want to maybe remove and redact some PII and load it into a dev system? That's a good use case for this. It's a good mechanism also to, for example, do an export of data that you want to share to someone else in a different organization. Here's a screenshot of what it looks like. I'm going to export the players table. I can pick the S3 bucket I want to put it into. It could be in this account or a different account. And I can do the current time by default, but I could also pick an earlier point in time in the preceding 35 days. I can export in DynamoDB JSON format or Amazon Ion, which is a superset of JSON that has more strong typing. So myself, I kind of like Ion. And you can pick how to encrypt it. You can use the standard S3 key or a KMS key. And you hit the export button, it does it. You don't even think about servers. So you're exporting data against a serverless system, and you're not seeing a server even when you're doing a bulk export. Another feature I wanted to mention is Particle, P-A-R-T-I-Q-L, pronounced particle, which I think is cute. This is a SQL interface. Basically, every NoSQL database grows until it has a SQL interface, and this is DynamoDB's. And why would you do this? If you're a developer coming from SQL and you say, I'm comfortable doing SQL queries, I don't want to learn a new interface, the interface being kind of a get item, I'll explain. Particle is for you. You still do your selects, you still do your updates, you still do your deletes the same way. You get the same performance. It's just another way to invoke it compared to what some people have called the vanilla DynamoDB API. So be aware of Particle. All right. So you combine all these enterprise features together. What can you do with them? Well, Capital One's a good case study, right? This is one of the largest banks in the US, about 25 years old, and they're known for being very innovative. They had a hard time innovating on their mainframe. They had 8 different data centers. They were mainframe bound. And so they looked at the AWS cloud. They were the first US bank to go all in on the cloud. And by doing this and using DynamoDB and all these enterprise features that I've talked about so far, you can see why these would be valuable for a bank. They were able to turn off the 8 data centers. Their quote is, the new solution is so much faster with an average response time of 55 milliseconds. And I think that's great that the queries are fast. I think it's also great that they're more nimble. Their word for it was nimbleness. Instead of being blocked as developers against the capabilities of the mainframe, they could go with microservices using DynamoDB as the data store and be able to do cool things like Capital One shopping, whereas you're doing a checkout, it'll look for coupon codes and see if it can give you a discount. That kind of thing was hard to do when they were tied to a mainframe in on-premise data centers. All right. So at this point, hopefully I've explained the high-level features, and hopefully I've whet your appetite a little bit. I'd like to now look at the key concepts of what's it like. How do you actually store data inside DynamoDB? So let's dig into the key concepts. So let's look at how SQL and NoSQL compare. SQL was born of a time, I think it was the 1970s, a little bit before my time. And at the time, storage was extremely expensive. NoSQL is a more modern invention. We're worried more about compute. Now, why is that? Both storage and compute have gotten a lot cheaper over the years, but storage has gotten dramatically cheaper compared to compute. In fact, I remember it was 1995, and I saw a terabyte. It took up a room. It was a robot that could pull tapes. And in my mind was blown. This room held a terabyte. My son is not impressed. He says, Dad, I have that on my phone. I'm aware. The world of data has changed. And so what that means is in SQL, what you didn't want to do is duplicate data. We were normalizing and joining, spending compute time to join data because we didn't want to write the same data more than once, right? That's one of the reasons we do the normalization. In NoSQL, we denormalize. We might have the same data written in multiple locations because it makes it faster and easier at query time and uses less compute. And that's a good trade-off for modern applications, all right? And really another difference is that SQL scales vertically while NoSQL scales horizontally. I'll show you that on the next slide. Here we have 2 different databases. The left is traditional SQL. Now, as you throw more traffic at traditional SQL, what do? Do you add more servers or do you make it a bigger server? In general, you make it a bigger server. And why is that? You do that mostly because your queries do a lot of joins, and you don't want to do joins across many different servers. The latency between servers slows you down. It just gets inefficient. Because of the joined nature of SQL, you want a bigger and bigger server. At some point, you can't make the server any bigger, though. And that's what hit Amazon.com back in 2004. In NoSQL, you do partitioning. And so as you add more data, you add more partitions. You can think of a partition being a bucket of different users. So a set of users going to partition 1, a set of users going to partition 2. You as a user, all your data goes into the same partition. I don't have to do cross-partition communication. Sometimes you do that in SQL. People will shard, right? We call this sharding. People do that in relational, but it's not as natural in relational databases because you're kind of creating duplicate copies of the whole world for different customers. Whereas in NoSQL, it's just a built-in part of the process, as I'm going to show you. Partitioning is just a part of the core database features. And the idea, that premise of that Dynamo paper in 2007 was there is a way to design data that's horizontally scalable. Here's a graph. this is your workload. You're doing very well. Good for you. Your volume's increasing, your reads are increasing, your writes are increasing. And this is what DynamoDB is doing to support you. It's increasing the amount of partitions. They're not servers. You don't see them as servers. On the back end, they're related to servers, but we increase your storage capabilities, your read capacity, and your write capacity. All right? Now let's get some nomenclature down. In DynamoDB, you have tables. The table has a name. It's unique per region. So you can have different tables in different regions. And if you have a table of the same name in different regions, they're still separate tables unless you've turned on global tables. Okay? Inside of a table, you have items. Sometimes you call them a row. Formally, they're called items, but if you say row, I'll understand what you're saying. And inside the items, you have attributes. That's what each one of these is. A1, A2, A3, A4, A5. Those are 5 different attributes, just sample names. In reality, A1 might be movies, and A2 might be actors. And so if I'm keeping track of which actors are in a movie, that's what those 2 attributes will be. And A3, A4, A5 is about the role and screen time or what have you. Notice that every item can be different. The schemas can be different. So that third one is very different than the first one. The second one is missing all extra attributes. That's okay. Okay, so it's not where you define a DDL and then you have your data. In this case, the data is self-describing. Every item has its own set of attributes. It's generally, there's not a lot of variation, but you definitely have different kinds of entities put into the same table, and that's just fine. Anytime you insert an item, you must have a partition key. The partition key is used, you hash it, and you therefore know which physical partition the data will be stored in. So you have to have partition key on an item to help say where it goes. So it could be the movie. Probably the easiest way to think about it is that a partition key is the customer ID. That's an extremely common partition key. So when you're storing data about a customer, partition key is going to be about this customer. The sort key is optional. When you define the table, you say whether or not you have a sort key. It's very common to have a sort key, and it's used to model one-to-many relationships. So if I have a customer as A1, all the sort keys will be the orders this customer made, the address of this customer, the phone number of this customer. Whatever it is that I want to have as an attribute on that customer can be done in the sort key. Okay? And when you're doing a query, you can specify the partition key, and you have a way to either specify the sort key exactly, or you can use bounds because it's sorted, and you can say, I want the keys that are above this value, below this value, between this value, start with this value, things like that. That's good for things like timestamp data. So if A1, this attribute, the partition key is a device, and A2, the sort key, is the timestamp of some action on that device, you could say, give me all the actions during this hour. And that is a query that uses the sort key and the inherent nature of sorting. You can also get, the last 10 or whatever. Here's a screenshot from the NoSQL Workbench, one of the sample data that they give you about accounts. So this partition key is an account number. And yeah, the name there is account hash number. You do that a lot of times, just kind of so that I can know that this is a partition key that is based on an account, because I can have another partition key that could be something else. And it's nice when I look at it that this was an account partition key, but maybe another one is an order partition key inside the same table. Under that partition key, I have 3 different sort keys I'm showing. The first one, which has chosen to have a sort key the same value as the partition key, which is a convention that says this is metadata about the item itself, tells me the account ID and the number and the first and the last name, the email ID. This is about this account. And then I have 2 different offers. And each one of those has its own distinct metadata that's about that particular offer. So you can see already, this is not like a relational database, right? Every item / row is different than the other ones. And I'm using as keys these strings, which have combined a prefix with a unique ID. And why would I do that? Well, let's look at how do I read data from DynamoDB. I have a bunch of different choices. Get item. When I do a get item, my goal is to get a singular item. I specify the primary key, which is the partition key and sort key combination, or if there's no sort key, then just the partition key. And it'll return 0 or 1 items. If it exists, it'll return it. If it doesn't, it gets 0. And when you do this, you consume a read capacity unit, right? Remember the on-demand and the provision mode. When you do a get item, it says, all right, well, that was an RCU. Really straightforward. A query is when you specify the partition key and optionally a sort key condition. All right. So on this last example, I could say, I want to find offers, which would be for this account, find me where the sort key starts with OFR hash, and that'll return me all the offers. If I don't give a sort key condition and I let all of them match, then I can get everything about this particular partition key, everything about this account, right? Or I can specify a particular offer range. Give me the 3 most recent offers, things like that. Okay, so that's based on the keys. You can add a filter condition. With a filter condition, you can query based on any attribute that exists, but it's not index optimized. Okay, and what that means is you're going to be pulling it off disk. Well, the service is going to be pulling it off disk and looking at it, seeing if it matches, and if it doesn't, it'll throw it away before giving it to you, but it still read it. And so it still consumes RCUs, whether or not the item matches the filter. So it's a good idea to try to put anything that you're going to query into the keys. The keys are about indexing and speed. A third way to retrieve the data is a scan. This is a table scan. You don't specify any keys. You just say, start scanning. All right. You can apply a filter, but it's going to scan the whole table and it will look at each item and see if it matches the filter before giving it to you or not. But this is just brute force scan. There's a time and a place for that, but don't do it lightly, right? Because you're going to be consuming enough RCUs to read every item out of the table. So you might do this for an end of month report or something that you can't do any other way, something that was a surprise query that had to be done. And so then here are a couple different things. On the right is all the different operation types. I covered get item, query, and scan. There's other ones. Batch get item, where you can specify numerous things to get, and instead of doing it as repeated singular requests, you can say here's n many that I want to retrieve. I can put and update and delete items. I can do a batch write item, which says here's a bunch of changes I want to make. And there's also 2 transact ones, transact get items and write items, which is to say I want to do this within a transaction boundary. I need it all to succeed or all to fail. Okay. On the left, we see the different data types. The center column is the DynamoDB types, and the left is maybe how you'd think about it as types. So a string is a string. An integer or a float in DynamoDB is just a number. A timestamp, people will do both. You can do a number as milliseconds since epoch or seconds since epoch, or you can do a string. If you do a string, I recommend a string that is sortable based on time, like the ISO 8601 format, where it's year, -month, -day, with an optional time. And if you do that, it works well as a sort key. Blobs are storable as binaries. Booleans are bools. Nulls and lists are supported. Sets are supported, and maps. Map is basically JSON. So you can have JSON as a data type in one of your attributes inside DynamoDB. If you're doing particle, remember particle, the SQL interface, then you have 3 additional operators. Execute statement. With this, you specify the select, insert, update, delete that you want. It runs it, singular. Batch execute statement. In this one, you can specify a list of items that you want to run as a batch. An execute transaction, which is a lot like batch execute statement, except you're saying, I want this run as a transaction. All or nothing semantics. Either they all work or they all fail together. Okay, so that's the way that you interface with DynamoDB. So at this point, you're able to store data. You understand there's a partition key and a sort key, but that's probably feeling fairly limited. You're thinking, but what if I want to look up by something else? Do I always have to filter? And the answer is no. We have secondary indexes. A secondary index is another way to look at the data. And you configure this and you say, all right, my base table has this partition and sort key, but for a GSI, I want a different one. I want maybe A2 to be my partition and A1 to be my sort. So if A1 was movies and A2 was the actor in the movie, that's nice because I can say, given a movie, give me all the actors. But what if I want to say, given an actor, give me all the movies? This GSI would support that because now it inverts those two. And you choose what you want to project into the index. So for that one, I'm doing keys only, which says for space savings and efficiency reasons, don't give me anything except for the keys. The second one is using A5 and A6, different attributes. It's making those into partition and sort. So maybe A5 is genre and A4 is year. And so now I want to look up all movies of a certain genre or all movies of a certain genre in a certain year. GSIs let me do that. And then the other one, A4, A5, switches them back. Maybe there I want to look up all movies by year or all movies by year and genre combination. Okay, so a GSI is another way to look at things. It uses the word global. It's not the same as global tables. This has nothing to do with the Earth being a globe. This is just that the partitions are global. You're not tied to staying within the same partition as you started. So the partition key on the GSIs can be different than the partition key of the base table. That's what global stands for here. You always get the item keys copied automatically for uniqueness. So when you say include A3, as that second GSI does, A3 is included, but you also automatically get A1 and A2 because it needs to know from which source table this came from, or which source item in the base table this came from, I should say. So here's an example of that credit card account. In this case, I happen to keep the same partition key of the account, but I made a new sort key. The name of the sort key here is GSI1SK. You see that happen a lot in DynamoDB because you want to maybe reuse that sort key for multiple purposes. So we do generic names of PK and SK and GSI1SK. This one is the combination of status and offer type. What that lets you do is now I can query for this account, give me all declined offers, give me all accepted offers, or give me all declined offers of type BAL or all declined offers of type promo, because I've done this hierarchical structure to the sort key. So query is a very powerful operator because given a partition key and any sort of constraint on the sort key, I can pull back everything about the account or just particular items about the account. So the base table has one point of view on the data and the GSI has an alternative point of view on the data. There are also local secondary indexes. It's local because in this case, the partition key has to be the same. And it's really called local because when it's stored in the same physical partition. So instead of being potentially scattered around to different partitions, in this case, it's always in the same partition. And so in this case, maybe A1 is the movie and A3 is the director. And so I want to look up by director. Maybe A4 is the producer and I want to look up movies producer combination. You name it, this is another way to look at it. Now, which one do you pick? A GSI or an LSI? Mostly people pick GSIs. And this kind of shows why. One is they're more flexible. You can create them at any time. Even after you've created the table, you can add a GSI, delete a GSI. LSIs, they exist from the point of table creation. When it comes to provisioning, LSIs share their capacity with the table. GSIs are independent of the table. So an LSI is kind of like data sitting right there next to the base table in the same partition. GSIs is a lot like a secondary table with just a different structure that is automatically having the data propagated from the base table into the GSI. LSIs limit the size of a particular partition key, which is an item collection. All the items under a partition key are called an item collection. With an LSI, because you're always writing to that same partition, you're capped at 10 gigabytes. And that's probably one of the biggest reasons people go toward GSIs. With GSIs, there's no size limit. If you aren't using LSIs, you can have under the same partition key unbounded amount of data. But if you have LSIs, you can only put 10 gigabytes under. There are 5 LSIs per table. There are 20 GSIs per table allowed. And LSIs, though, they have strong consistency, which means if I do a write to the base table, the LSI will update as well. It will have been updated by the time you get the success back. With GSIs, it's done with eventual consistency. So you do an update to the base table, and it will shortly, typically in milliseconds, but not guaranteed in milliseconds, be propagated to the GSI. So that's the difference between the two. And that concludes the value of DynamoDB and the key concepts. And I'll pause here for questions, and then we'll resume with the more advanced content, digging into how does it actually work on the back end. Thank you very much.